General Chemistry 1. Let's turn. This study is divided into two lessons, the atomic structure and gas behavior. In the atomic structure, we will tackle about the planetary model, quantum model, and electron configuration. While in the gas behavior, we will tackle about different gas law, the Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, ideal gas law, Dalton's law of partial pressure, Avogadro's law, Graham's law, and the gas stoichiometry. So we will start this lesson by knowing what is atomic structure.
Atomic structure. From the word itself, atomic structure is the structure of an atom. An atom comprises of three particles, protons with positive charge, neutrons with neutral charge, and electrons with negative charge.
The planetary model of an atom is also known as Bohr model. The Bohr model was proposed by Niels Bohr in the year 1930. In this model, the electrons travel around the nucleus in a circular orbit or shell. The planetary model is a model in which the positively charged nucleus is orbited by the negatively charged electrons. Since the Bohr model is just the modification of the model before it, sometimes it is referred to as the Rutherford-Bohr model. The primary model contains some errors, but it is important because it describes or represents most of the accepted features of atomic theory without using the high-level mathematics like in the modern version. The electrons have a set size of energy where the smallest energy has the smallest size and the biggest energy level has the biggest size.
The quantum mechanical model of the atom views electrons within an atom as waves, not as particles as previously believed. Because of this, electrons can be described as having a high probability of residing in specific orbitals or regions of space within the atom. The quantum model determines the allowed energies an electron can have and how likely it is to find the electron in various locations around the nucleus. Erwin Schrödinger proposed the quantum mechanical model of the atom, which treats electrons as matter waves. It is created when the Bohr model failed to account for the wave properties of the electron. So Schrödinger utilized his equation to predict the probability of finding electron within a specific orbital in the atom. Within each energy level, there are sublevels. The sublevels are labeled as S, P, D, F. And within each sublevel, there are orbitals. This is the final location where electrons reside. Quantum number. It is used to determine the electron configuration of an atom and the probable location of the atom's electron. There are different quantum numbers. First, the principal quantum number. It describes the energy of an electron and the most probable distance of an electron from the nucleus and labeled as symbol n. Next, the azimuthal quantum number. It is described the shape of the orbitals, also known as orbital angular momentum quantum number and labeled as L. Magnetic quantum number is primarily determines the number of orbitals and the orientation of orbitals in a given subshell. Consequently, it is dependent on the orbital angular momentum quantum number, also known as the azimuthal quantum number. And the last is the spin quantum number. This refers to the spin of the electron, which can be either up or down.
Electron configuration is the arrangement of electrons in an atom's orbital, which determine the atom's chemical properties. Electrons are distributed in different energy levels or shells around the nucleus, each of which contains specific sublevels or subshells. Energy level or shell. Electrons occupy shells, each represented by a principal quantum number n is equals to 1, 2, 3, etc. The first shell, n is equals to 1, is closest to the nucleus and each subsequent shell is further away. The maximum number of electrons a shell can hold is given by 2 and 2. For example, first shell n is equals to 1, which can hold 2 electrons. Second shell n is equals to 2, which can hold 8 electrons. Third shell n is equals to 3, which can hold 18 electrons. And lastly, fourth shell, which is n is equals to 4, which can hold 32 electrons. Sublevels or subshells. Each shell contains subshells designated as S, P, D, and F, each holding a specific number of electrons. S, 1 orbital, which can hold 2 electrons. P, 3 orbitals, which can hold 6 electrons. D, 5 orbitals, which can hold 10 electrons. F, 7 orbitals, which can hold 14 electrons. Order of filling. Electrons fill orbitals in order of increasing energy, which follows the off-both principle. The order of filling is usually remembered by the n+1 rule. For example, 1s fills before 2s and 4s fills before 3d. Hund's rule. Electrons occupy the generated orbitals or orbitals of the same energy. Singui before pairing up to reduce repulsion.
Pauli's exclusion. No two electrons can have the same set of quantum numbers, thus each orbital can hold a maximum of 2 electrons with opposite spin.
Boyle's law is a basic law in chemistry, describing the behavior of a gas held at a constant temperature. The law discovered by Robert A. Boyle in 1662 states that at a fixed temperature, the volume of gas is inversely proportional to the pressure exerted by the gas. Boyle's law can be written as PV equals K, where P is the pressure of the gas and V is the volume of the gas and K is a constant. An example of Boyle's law in action can be seen in a balloon. Air is blown into the balloon. The pressure of that air pushes on the rubber, making the balloon expand. Here are the formula of Boyle's law. P1, B1 equals P2, B2. The P1 is the first pressure, the P2 is the second pressure, and the V1 is the first volume, and the V2 is the second volume. I will give some example problem to solve. Boyle's law sample problem. A sample of oxygen gas has a volume of 150 ml when its pressure is 0.947 atmosphere. What will the volume of the gas be at a pressure of 0.987 atmosphere if the temperature does not change? So first we must find the given. The P1 is the 0.947 atmosphere, the V1 is 150 ml, and the P2 is 0.987 atmosphere, and the volume 2 is what is asked. In the first volume, 150 ml is on ml. It should be in liter, so we must convert in liter. 150 divide 100 is 1.5. So to solve this, we must write the formula of Boyle's law. P1, B1 equals P2 and P2. So after that, we will write the given. 0.947 times 1.5 divided by 0.987 is equal to 144 liter of O2. And let's proceed to the second example. Example 2. Under a pressure of 0.988 atmosphere, helium fills a balloon to 1 liter. What would the pressure be if the volume of the balloon stretched to 2 liter? Do the same like we do in the first problem. We will find the given and write the formula of Boyle's law and multiply and divide them, then the answer will be 0.494 atmosphere.
Charles' law is one of the gas laws that describes the relationship between the volume and temperature of a gas at constant pressure. It states that the volume of a given mass of a gas is directly proportional to its absolute temperature, measured in Kelvin, provided the pressure remains constant. As the temperature increases, the volume of the gas decreases, and also the temperature must be in Kelvin because negative temperatures in Celsius could yield nonsensical negative volume. Charles' law is named after Jacques Charles, a French physicist and inventor. He formulated this law around 1787, though he never published his findings. The law was later popularized and formally published by Joseph Louis Gay-Lussac in 1802, who credited Charles with the discovery. Thus, while Jacques Charles discovered the law, Gay-Lussac helped bring it to wider scientific recognition. Formula: V1 over T1 is equals V2 over T2. V is the volume of the gas, T is the temperature in Kelvin. Subscript 1 and 2 represent the initial and final states, respectively. Real-life examples of Charles' law. 1. Hot air balloons. When the air inside the balloons is heated, it expands, increasing the balloon's volume. This makes the balloon less dense than the surrounding air, causing it to rise as the air cools. The volume decreases and the balloon descends.
Gay-Lussac's law. The Gay-Lussac's law states that the pressure exerted by a gas whose mass is known and volume is kept constant varies accordingly with the temperature of a gas. Therefore, it is one of the most important properties of gases.
The definition of Gay-Lussac's law describes the relationship between pressure and temperature in gases. It states that, at constant volume, the pressure of gas is directly proportional to the absolute temperature.
Applications of Gay-Lussac's law can be listed as follows. First, if we heat an aerosol can, the increased temperature causes the gas to change. According to Gay-Lussac, the pressure built up in a can may result in an explosion. And second, another example of the release of heat is the process of firing a bullet. We all know that a gun is fired with the help of gunpowder. Then the gunpowder burns and the bullet is fired. This is because when the gunpowder burns, the gases trapped inside are heated. This increase in temperature causes the pressure to increase. According to Gay-Lussac's law, hence as a result of superheated gases, the bullet is pushed forward with a tremendous force towards the gun's barrel. Third, we can also view the application of Gay-Lussac's law in the example of burning an automobile tire. As the tire heated, the heat spreads over the rubber and other constituents. Due to this, the pressure increased. The increased pressure cannot be contained with the tire. The tire then explodes as its walls weaken compared to the increased pressure.
Number 4. While cooking, the increased pressure in a pressure cooker is another example of Gay-Lussac law. As the contents of the pressure cooker are heated, the gases trapped inside, such as the steam, exert pressure. This is because the temperature of the gases, such as the steam, is directly proportional to the pressure exerted. This causes the steam to be released through an external part of the pressure cooker. The higher the temperature and pressure inside of the container, the shorter the time the food will cook.
I'll discuss about the combined gas laws. The combined gas laws combines three individual gas laws, which is the Boyle's law, Charles' law, and Gay-Lussac's law. It describes the relationship between the pressure, volume, and temperature of a gas when the amount of gas remains constant. So we have a problem that will represent the combined gas law. Okay, problem number 1. A balloon contains 2.0 liter of air at 300 K, which is 300 Kelvin, and 1.0 atm pressure. If the balloon is heated to 350 Kelvin and the pressure increases to 1.2 atm, what is the new volume? So our first step is we're going to write down the given values, which is the V1 is equal to 2.0 liter, T1 is equal to 300 Kelvin, P1 is equal to 1.0 atm, or T2 is 350 Kelvin, P2 is equals to 1.2 atm, and our missing is the V2, which is the volume. So the next thing we're going to do is derive the formula. So our formula for combined gas laws is V2 is equals to P1 times V1 times T2 divided by T1 times P2. So we're just gonna distribute the values. So P1 is equals to 1.0 times V1, which is the 2.0, times T2, 350, divided by T1, which is the 300, times P2, which is the 1.2. So 1.0 times 2.0 times 350 is equals to 700. 300 times 1.2 is equals to 360. 700 divided by 360 is equals to 1.94 liters. So if the balloon is heated to 350 Kelvin and the pressure increases to 1.2 atm, our new volume is equals to 1.94 liters.
Ideal gas law is the law that the product of pressure and volume of one gram molecule of ideal gas is equal to the product of absolute temperature of the gas and universal gas constant. The formula of ideal gas law is QB is equal to nRT, which P is pressure, V is volume, N is amount of substance, and R ideal gas constant, and T is the temperature. In examining ideal gas, we were able to discuss four variables. First is pressure. This is the force of gas exerting in container, or rather how much particles are hitting the sides. 2. Temperature. This is the amount of heat energy. 3. Volume. How big is container? 4. Moles. How many particles in the container? Ideal gas law relation between pressure, volume, temperature of a gas in the limit of pressure and high temperature, such that the molecules of a gas move almost independently of each other. So, this is an example of ideal gas law. A gas occupies a volume of 5.0 liter at a pressure of 3.0 atm and a temperature of 400 Kelvin. How many moles of gas are present?
P is 3.0 atm and V is equal to 5.0 liter. N is unknown. R is 0.0821, which is constant. T is 400 Kelvin. So bring down the given numbers. 3 liters times 5 atm is equals to 15. 3 times 5 is equals to 15, and 0.0821 times 400 Kelvin is 32.84. So if then divide it, magiging 0.45 moles.
Dalton's law is a gas law which states that the total pressure of a mixture of gases is equal to the sum of all the partial pressure of component gases. For example, if we have a container that holds four gases, which is oxygen, carbon dioxide, hydrogen, and nitrogen, with the atmospheric pressures of 2 atm, 4 atm, 5 atm, and 3 atm respectively, how are we going to find out the total pressure of a mixture of these gases? So, we need to add all up the partial pressures of each gases, which is 2 atm, 4 atm, 5 atm, and 3 atm, so we can lead or conclude to 14 atm, which is the total pressure computed. To solve for the partial pressure of each gas, we need to divide the number of moles to the total number of moles of all the gases involved in the mixture times the total pressure of a given mixture. For example, we have the mixture of 3 moles of H2, 2 moles of N2, and 5 moles of CO2 that exerts a total pressure of 700 torr. What is the partial pressure of each gas? To find out, we have 3 moles of H2 divided by 10 moles, which is the total number of moles of all the gases involved in the mixture times 700 torr, which will lead us to 210 torr. Next, we have the N2. We have 2 moles all over 10 moles times 700 torr, that will lead us to 140 torr. The last one is the CO2. We have 5 moles divided by 10 moles times 700 torr, which will lead us to 350 torr.
Avogadro's law states that under identical condition of temperature and pressure, equal volume of all gases contain the same number of molecules. This means that the volume of a gas is directly proportional to the number of molecules, or what we call moles of a gas present, assuming temperature and pressure are constant, where V is the volume of the gas, M is the number of mole of gas, K is a constant for a given temperature and pressure. So I prepared a word problem so that we can calculate what volume is. So let's proceed to that problem. A balloon contains 2 moles of helium gas at a constant temperature and pressure, occupying a volume of 10 liters. How much volume will the balloon occupy if the number of moles of helium gas is increased to 4 moles, assuming temperature and pressure remains constant?
Our formula is V2 equal V1 times N1 over N1. Ang volume ng ating V1 ay 10 liters, while ang ating N2 is 4 moles, and ang ating N1 is 2 mole. Then, i-multiply natin ng V1 at saka ang N2. So, makakakuha tayo dito ng 40, ika-cancel out natin ng mole, ang ilalagay natin is liters. And then 40 divided by 2 is 20. So ang volume ng ating V2 is 20 liters.
Graham's law of diffusion explains the relationship between the rates of diffusion or effusion of gases and their molar masses. It states that the rate of diffusion of a gas is inversely proportional to the square root of its molar mass. Mathematically, this can be expressed as Ra over Rb is equal to the square root of molar mass A over molar mass B, where Ra and Rb are the rates of diffusion of gas 1 and gas 2, respectively. Molar mass A and molar mass B are the molar masses of gas 1 and gas 2, respectively. And by the way, lighter gases diffuses faster because gases with smaller molar masses will diffuse more quickly than those with larger molar masses.
Stoichiometry involves the calculation of volume, masses, or moles of gases involved in chemical reactions. Based on the relationships defined by a balanced chemical equation, it relies on the principles of ideal gas law, PV and RT, where P is pressure, V is volume, N is the number of moles, R is the gas constant, and T is temperature. At standard temperature and pressure, STP 0 Celsius and 1 atm, 1 mole of any ideal gas occupies 22.4 liters. By using these principles, stoichiometric calculations allow us to predict the amount of gas consumed or produced during a reaction. In practical applications, gas stoichiometry connects the behavior of gases with other states of matter in chemical reactions. For instance, if a reaction produces a gas, the volume of that gas can be calculated from the moles produced provided temperature and pressure are known. Similarly, the amount of reactants required to produce a specific gas volume can also be determined. This is crucial in fields like industrial chemistry, environmental science, and engineering, where precise control of reactants and products is essential. Adjustments are made from real gases by incorporating corrections, as real gases deviate from ideal behavior under high pressures or low temperatures.
A non-reversible reaction uses the reactants to form the products. One of the most common forms of non-reversible reaction is combustion. To understand how the ideal gas law applies to reactions, we shall use a non-reversible reaction as an example. So for our example, the decomposition of hydrogen peroxide to water and oxygen gas. If 4.0 grams of hydrogen peroxide is placed within a sealed 250 milliliter container at 500 Kelvin, what is the pressure of the oxygen gas produced in atmospheres? First, we need to determine the moles of O2 produced. 4 grams of hydrogen peroxide divided by the molar mass of H2O2 is equals to 0.117. Divided by 2 is equals to 0.0588 mole of O2. with the moles of oxygen determined. We can now use the ideal gas law to determine the pressure. So for our formula, it is PB is equals to nRT. The volume 250 ml is equals to 0.25 in liters. And temperature 500 Kelvin is already given to us. And R is equals to 0.0821 and it is constant. And so for Rn, it is 0.0588 which we solve. 0.0588 times 0.0821 times 500 is equals to 2.41374 divided by 0.25 is equals to 9.65 atm. By simply using calculator, we can get the answer 9.65.
And that's it. Our study will end it up here. Thank you.